The subject of linear algebra has its origins in the study of systems of linear equations. Therefore, it is natural that we begin our course with a discussion on linear systems of equations. In the beginning, we shall keep our discussions not very rigorous, but only to motivate the basic and fundamental questions that we will be discussing in this course. So, let us begin with a simple system of linear equations. Consider the system of linear equation x plus 3y equal to 6 and x minus y equal to 2. It is very easy to see that x equal to 3 and y equal to 1 is a solution of this system, and more importantly it is the only solution for this system. We can also geometrically interpret this as the intersection point of two lines, one of which is represented by the equation x plus 3y equal to 6, the other one is represented by the equation x minus y equal to 2, and 3, 1 are the coordinates of the points of intersection of these 2 points. Looked at from this point of view, we in general can consider a system of 2 equations in 2 unknowns and think of them as the intersection point of these 2 lines. However, we see therefore that this could lead to many situations. One, the lines intersect at one point, or the 2 lines coincide, or the 2 lines are parallel. Therefore, when we have a pair of 2 lines, we can have these 3 situations. In the case 1, when the lines intersect at one point, we see that there is a unique solution for the system given by the coordinates of the point of intersection. When the lines coincide, we see that there are an infinite number of solutions for the system, because every point represents a solution of the system. When the lines are parallel, we know that they do not meet, and therefore, there is no solution for the system. Thus, we see that we could end up with several situations, namely lines intersecting at one point, lines coinciding with each other and therefore giving infinite number of solutions, or lines being parallel, therefore there is no solution. And therefore, in general a system of 2 equations in 2 unknowns can have exactly one solution, or can have an infinite number of solutions, or can have no solution whatsoever. Now, it is clear from this discussion that we could also have a situation with no solutions. In general, we would be interested in considering m equations in n unknowns. This is generally written in the notation a11 x1 plus a12 x2 plus a1n xn equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn equal to b2, and so on, and the last equation is am1 x1 plus am2 x2 plus etc. plus amn xn equal to bm. Here in the A's, the first index, for example in a22 or in am2 or in amn, the first index refers to the number of the equation. So, in the second equation, all of them will have the first index as 2, a21, a22, a2n, and the second index for the A's refers to which unknown they are referring to. a11 x1 means it is the coefficient of the first unknown, a22 x2 means it is the coefficient of the second unknown, Amn xn means it is the coefficient of the nth unknown. Such a system is what we will be considering in general. A system of this type is written in a compact form in matrix notation as follows. We denote by A the matrix which is m rows and n columns with the entries as Aij. So, Aij is the coefficient coming from the ith equation corresponding to the jth unknown. We denote by X the single column matrix which refers to the unknowns x1, x2, xn, and by B the single column matrix B1, B2, Bm which corresponds to the right hand side of this equation. So, with this notation, in matrix notation we can write the system as Ax equal to B. So, in general therefore, we are interested in the system Ax equal to B. What is the main problem? The main problem is given m by n matrix A, this is given. Then for different B, find solution. That is our first fundamental problem of linear systems of equations. We have seen that even in 2 by 2 systems, we could have a situation when there are no solutions, and therefore, the first main question that we have to answer is what is the condition that B should satisfy for a solution to exist. This is one of the most fundamental existence questions. Given the system Ax equal to B, that means given the matrix A, for what values of B will we have the solution for the system Ax equal to B, or in other words what condition should B satisfy in order that the system Ax equal to B has a solution. Now, therefore, given the system, the first question that we will ask is what is this criterion for existence. Suppose we have found this. So, suppose we have the condition C, this condition C. Then given any problem, any B, any problem like this Ax equal to B, the first question that we will ask is, does B satisfy C? Now, obviously, there are two possible answers for this. We may guess an answer yes and we may get an answer no. So, let us discuss what we can do in both these situations. When the answer is yes, what is the conclusion that we can make? We can say solution exists. When we say solution, we mean refer to the system Ax equal to B. So, we know that the solution exists. Then the fundamental question is how many solutions exist? This question arises because we have seen in the 2 by 2 system there are situations where we can get exactly one solution or situations where we can get infinitely many solutions. So, the answers are going to be 1 or infinitely many. So, the question then is, when do we get one solution? Under what conditions do we get one solution? Then we had these answers, one solution, infinitely many, and the question when it is 1, under what conditions we get one solutions, under what conditions we get infinitely many solutions. Now, having answered this question, when there is only one solution, we want to find the solution, the unique solution which we know exists, we have to find. When there are infinitely many solutions, what is the structure of all these solutions? That is the next question that we will have to answer. Now, having got the structure, we have a problem of plenty in this problem situation where we have so many solutions. Is there some way of choosing one solution? So, criterion to choose a unique representative. Among all these solutions, we must choose a unique representative. Then finally, find the unique representative. So, therefore, when we are in a situation where B satisfies the consistency condition, solutions are guaranteed, then we are in several situations, one solution or infinitely many solutions. In the case of one solution, we would like to eventually find the solution. In the case of infinitely many solutions, we would like to find some criterion by which we choose a unique representative solution and get that representative solution. Now, the problem is what happens if B does not satisfy the criterion C. In that case, when B does not satisfy the criterion C, then what can we conclude? We can only conclude no solution for A x equal to B, because C was the criterion for a solution to exist and B does not satisfy it, and therefore, we would like to conclude that there cannot be any solution. If there is no solution, what do we do? For this, we would like to analyze what exactly does the fact that there is no solution imply. So, therefore, what do we mean by no solution? This means that whatever x I choose and calculate Ax is not going to be equal to B for any x. Ax is not going to be equal to B for any x. That means B minus Ax is not going to be the 0 column matrix for any x. This means if I look at B minus Ax, I would have liked this to be 0 if x were a solution, but since x cannot be solution for any x, B minus x is not equal to 0 vector, 0 column matrix for any x, and therefore, if we take x as a solution, there is going to be an error. That error is given by this difference B minus Ax. Now, what is the general idea when you get error? The general idea when you get error is would like to minimize that error. How do I minimize this error? We quantify this error first. The error is in the form of a column matrix. We now quantify this error by a number. How do we do this? We look at the ith coordinate of the error, that is a number, take the square of that and now do this for every coordinate from I equal to 1 to m and add this. This gives us the square error from each term added together in the entry of the error vector. Now, we would like to minimize this. we would like to minimize this quantified error. So, can we do it? We shall see later that this is possible, and this leads us to the notion of the least square solution. What do we mean by a least square solution? So, suppose B does not satisfy the consistency condition C, no solution exists for Ax equal to B, then a column matrix X, we will call it L to denote the fact that it is going to be a least square solution, is called a least square solution if it minimizes the squares of the error. What does it mean? If you now look at the error obtained by taking this x and calculate the error in each entry in the error matrix, square it and add all the errors, that error should be the least among all possible errors. That is, if I take any vector Ax and calculate the error, it cannot be less than this. So, the least square solution is a solution which minimizes this particular quantification of the error. Okay. So, obviously, therefore, different notions of errors quantification could lead us to different types of error solutions, but we will be concentrating only on this least square solution. So, therefore, in the case of we can show that we always can get a least square solution if B does not satisfy C. If B does not satisfy C, we can show that there is a least square solution, and therefore, let us get back to the situation. The next question therefore, we would ask is how many least square solutions? Now, we get into a loop again, just as in the case when B satisfied C, there was a solution. Now, B does not satisfy C, there is a least square solution. In the case B satisfied, how many we ask? There are one or infinitely many. In this case also, we get either one least square solution or infinitely many least square solution. Now, therefore, the question is again, when does this happen and when does this happen? Having answered that, the question that we would like to answer is finally find the least square solution. In the case of infinitely many, remember that in the case of infinitely many solutions, when B satisfied C, we said we want a criterion for choosing a representative. Again, here we would ask for choosing a representative, criterion for a representative, because we have a problem of plenty, we have too many least square solutions, eventually we have to pick one solution. So, we need some criterion for picking. Having got that criterion, our final goal should be find the representative least square solution. So, therefore, while dealing with a linear system of equations, there are several questions that arise. Now, one of our major goals will be to get the answers to all these questions and look at the generalizations of all these questions that are possible, and we will develop the correct mathematical framework in which we should ask these questions. Now, let us therefore understand that a linear system of equation is going to involve several questions which require fundamental answers, and there are fundamental questions which will require the theory to get the answers, which would also require techniques to get the solution. Let us next get back to the question of how do we handle all these questions. What is the natural way to go about finding the answers? The natural way that the mathematician does is, whenever he has a problem which is difficult to solve, look at the simplest version of the problem and see what are the mechanisms involved in the simplest version, and the knowledge gained from that is going to help him to handle the most difficult or the most general situation. So, the first thing that we would like to ask is, what are easy systems? That is, systems which can be easily solved, for which all the answers can be given without much hard work. To answer this question, we must first understand why are the general systems difficult. Why are the general systems difficult? The difficulty lies in the fact that each equation involves every one of the variables, or probably each equation will involve several variables, and therefore, no equation on its own is able to help you to determine one of the unknowns. This is what we call as the variables or the unknowns are all coupled in a general system, and this is what makes, what do we mean by solving the system? We want to get x1 separately, we want to get x2 separately, we want to get x3 separately, x4 separately, and so on. That means we want to uncouple them. That is essentially what is meant by solving a system. We want to uncouple all the variables, and therefore, it is this uncoupling process that looks very complicated, because the coupling, the more the coupling, the more number of variables each one of these equations involves, the more complicated the uncoupling is going to be. Therefore, let us first look at a system where such an uncoupling is easy. So, a system where uncoupling is easy. What is such a system? Obviously, there is no coupling at all. Right in the beginning, in this equation itself there was no coupling, then that is an easy system, because the work is already done. So, a system is, that is a system where there is no coupling. What is such a system? Such a system, each equation involves only one of the unknowns. Okay. So, each equation involves only one unknown, let us look at the simple situation where the first equation involves the first unknown, second equation involves the second unknown, and the nth equation involves n unknown. So, let us even make it clear that there are n unknowns, we have n equations, and the ith equation involves ith unknown. So, n equations, n unknowns, ith equation involves ith unknown x I. So, how does such a system look like? It will involve the ith equation will involve only the ith unknown. So, we will have the first equation will be d1 x1 equal to b1, d2 x2 equal to b2. Note, the first equation involves only x1, the second equation involves only x2, the ith equation involves only xi and so on, and the nth equation involves xn. So, this is one of the simplest situations of a system. We have n equations, we have n unknowns, the variables or the unknowns are all completely decoupled, and ith equation involves only ith unknown. So, therefore, we can easily solve, try to solve at least these equations. Let us look at how we would go about solving it. If you want to solve the ith equation, we would like to write xi equal to bi by di, but then we can't divide by di and if di is 0. So, the equations which are where the di's are 0 are going to be problematic. So, let us separate this out. So, let us without loss of generality assume the first row of the d's are not 0 and the remaining d's are all 0. In that case, at least we get from the first equation x1 equal to b1 by d1 and so on, and the rowth equation gives x row equal to b row by d row. But now, if you look at the row plus 1th equation, the left hand side for the equation will be 0, whereas the right hand side will be b row plus 1, and therefore, a solution will exist when both the sides will be 0 only, and therefore, b row plus 1 must be equal to 0. Continuing this process, we get the consistency condition must be b row plus 1, b row plus 2 etc. b n must all be 0. So, therefore, a system like this will have a solution if and only if the row whenever there is a 0 on the left hand side, there the corresponding b's are also 0. So, we are assuming that the left hand sides are all 0 from the row plus 1th equation onwards, and therefore, the b's must all be 0 from the row plus 1th entry onwards. So, therefore, the consistency condition for such a system becomes b row plus 1, b row plus 2, b n are all 0. Now, what do we get from this? If b satisfies this condition, what does that imply? Then the first row unknowns x1 is b1 by d1, x2 is b2 by d2, x row is b row by d row, these are got, and the remaining variables whatever value I choose, the equations only give 0 equal to 0, 0 equal to 0, 0 equal to 0. So, what we get is xi's are given as bi by di for 1 less than or equal to I less than or equal to rho, and xi is arbitrarily chosen, can be arbitrarily chosen for rho plus 1 less than or equal to I less than or equal to m. So, now remember the first question we asked was, what is the consistency condition or what are the conditions under which the system has a solution. For that, now we have an answer. The conditions are whenever d rho plus 1 dn's are 0, the corresponding b rho plus 1 bn's must be 0. That is a consistency condition. Now, when that condition is known, given a b, we ask does b satisfy this condition. Suppose b satisfies this condition, then we have the answer that the solution must be of the form xi equal to bi by di for 1 less than or equal to I less than or equal to rho, and xi equal to any arbitrary value for I between rho plus 1 and n. Now, this says there are lots of arbitrary values that we can choose for xi's from rho plus 1 onwards. Therefore, even if rho is n minus 1, then there is an I for which xi can take several values, and therefore, we will get an infinite number of solutions. And when will therefore, we get a unique solution? When all the xi's are uniquely determined, that will happen when rho is equal to n. So, what is our conclusion out of this? We get a unique solution when rho equal to n. So, unique solution when rho equal to n. Remember the question we asked, when does it happen unique solution? We have the answer for this, when rho equal to n. And then what is the solution? And the solution is xi equal to bi by d. Thus, in this case, in this simple system, at least when rho equal to n, we have all the answers. When is the solution not unique? That is infinite number of solutions. When rho is less than n, since we can choose x rho plus 1 x n arbitrarily. So, what is the structure of the solution? The structure of the solution is xi equal to bi by di for 1 less than or equal to I less than or equal to rho, xi arbitrary for rho plus 1 less than or equal to I less than or equal to m. Now, we have not answered one further question. Whenever we have infinite number of solutions, we would like to have a criterion by which we choose one solution as the representative solution. We will come back to this question a little later. It is not very difficult, but we will handle them all together. But the moral of the story of a discussion of this simple problem is that when we have a system d I x I equal to b I 1 less than or equal to I less than or equal to n, a system of n equations in n unknowns where the variables are all uncoupled, most of our answers can be easily got. Now, what is the structure of this system? The important thing in this system is the matrix A for such a system is a diagonal matrix, because A11 is the coefficient of x1 and that is d1, and the remaining coefficients in the first equations are all 0. Similarly, the second coefficient in the second equation is 2 and all others are d2 and all others are 0 and so on, and therefore, the coefficient matrix is a diagonal matrix. So, the moral of our discussion for such special easy system is diagonal systems are easy to handle. So, let us put it that way. So, therefore, the diagonal systems are easy to handle. We will be discussing this one more time in greater detail, more rigorous situations, more rigorous language, but as a simple motivation we have seen that when a system is diagonal, it is easy to handle. Almost all the questions come out, the answers come out fairly straightforward. Now, therefore, what should be our next move? The idea always is, if you know how to solve or how to handle one particular problem, the next level complex problem would be attempted to be brought down to this easy level. So, given a general system n by n system, let us stick to n equations in n unknowns, the easier version. So, given a general n by n system A x equal to b, can we reduce it to the analysis of a diagonal system? Can we reduce this to the analysis of a diagonal system? What do we mean by this, or how can we go about getting to this diagonal system? This is where we like to introduce the idea of change of variables. Suppose we have this system A x equal to b, A is an n by n matrix, B is an n by 1 column vector, x is an n by 1 column vector, which has to be found. We want to know what is x, such that A x equal to b. Now, we introduce a new variable y, which is equal to say some k times x, where k is an n by n matrix. Now, what is the idea? The idea is we would somehow try to get an equation to y which is easy to solve. Now, what is the use? The idea is if I know y, I can find an x. How do I know x from y? Well, I would be able to write x is equal to k inverse y, provided k is an invertible matrix. So, we will say k is an n by n invertible matrix. So, we introduce a change of variables y equal to k x, where k is an invertible n by n matrix, then x becomes k inverse y, or in a standard most of these books will use the notation p y. So, we will say x is equal to p y. Now, therefore, b also we can change as some p z. So, we have introduced two change of variables, y will be the new unknown and z will be the new right hand side, new known. So, what happens to the system? The system becomes A times x, x is p y equal to p z, because b is equal to p z. Now, p is invertible because p is k inverse and k is invertible. So, this implies p inverse A p y is equal to z. Therefore, the equation for y becomes p inverse A p y equal to z. We will call p inverse A p y as some t. So, that becomes t y equal to Z. Now, if we know y, then we get x as x is equal to k inverse y. So, therefore, knowing y, we can get x as p y. So, the problem therefore is, can we solve y? We can solve y if T were a simple matrix. What do we mean by a simple matrix? Namely, the diagonal matrix. So, suppose we can make T diagonal. So, we have T y equal to Z, where T equal to P inverse A P and Z is equal to P inverse B, or B is equal to P Z. Suppose we can find P such that T equal to P inverse A P is a diagonal matrix. Then the system for y is a diagonal system and we have seen that diagonal systems are easy to handle. So, system for y is easy to handle, and since the knowledge of y we can get x, it says the system, the given system A x equal to b can be handled. Therefore, the fundamental question that we have made is, if this passage of change of variables works, then any system of n equations in n unknowns can be converted to a diagonal system. Therefore, the fundamental question is, does this sort of change of variable work? So, the given given a matrix A, can we make the matrix into a diagonal matrix by a transformation of the form P inverse A P. So, given A, can we find P an invertible matrix such that P inverse A P is a diagonal matrix? This is another fundamental question in linear algebra. This is called the diagonalization process of a matrix, and we will look at the answer to this question as we go along as one of the most fundamental problems in linear algebra about diagonalization of these matrices. Now, we shall see with a few examples that these diagonalization problems create the diagonalization questions create certain problems, namely that not all matrices can be diagonalized, and hence we get into a fundamental question that this process of converting a general system of equations to a diagonal system may not always work. So, it turns out that for certain class of matrices, certain types of matrices, we can find a P such that P inverse A P is diagonal, and for certain types of matrices we cannot find a P such that P inverse A P is diagonal. Now, therefore, it raises the question, under what conditions can a matrix A provide you with a P such that P inverse A P is diagonal? we have to now one more criterion to be found. Remember, just as we said, what is the condition B should satisfy in order that Ax equal to B as a solution. Analogously, now we are asking what is a criterion that A should satisfy in order that P inverse AP is a diagonal matrix. Consequently, the moment we find this criterion, we will again ask a series of questions, namely, given a matrix A, check whether it satisfies this criterion. If it does, the fundamental question therefore is, given n by n matrix A, can we find invertible P such that P inverse AP is a diagonal matrix. The answer to this question is very complex, and this leads to a lot of very interesting canonical forms of matrices, and we shall be discussing all of them, at least several of them. The first thing is to look at an example. If you look at this matrix, we leave it as an exercise to verify that no P which is invertible 2 by 2 exists such that P inverse AP is diagonal. And therefore, we are into certain difficulties, that not all matrices possess this diagonalization property. Therefore, the fundamental question is, what criterion should A satisfy in order that such a P exists? Let us call again such a criterion, say criterion C. Okay. Now, having got this criterion, the question therefore would be, if the criterion is satisfied, we will be able to do this diagonalization. If the criterion is not satisfied, we will not be able to do this diagonalization. Now, the diagonalization non-possibility not possible leads to two important things which we will be discussing in the class. One is the so called Jordan canonical form, and the other, which is very useful in applications, called the singular value decomposition. Both these are very important. What is this Jordan canonical form? It is, we have A. In general, there may not be any P such that P inverse AP is a diagonal matrix. So, what do we do? So, we would say try to find a P such that P inverse AP is as close to a diagonal matrix as possible. So, find a P such that P inverse AP is as close to a diagonal matrix as possible. Now, what do we mean by as close? Now, making these things formal, precise leads you to the notion of Jordan canonical form. What is the singular value decomposition? This is very important for us because so far we have been discussing a system of equations where we have n unknowns and n equations. But when we looked at the singular, when you look at the singular value decomposition, we will see that this also now allows us to generalize this notion of singular value decomposition to rectangular systems where the number of equations may not be equal to the number of unknowns. So, this is allows for generalization to rectangular systems. Now, what is this? What is this singular value decomposition? Now, recall that we had the system A x equal to b and we introduced the transformation of variable x equal to p y, b equal to p z. Now, here we have used the same matrix P to transform x as well as y. Now, suppose we use a change of variables x equal to p y and b equal to q z, where p q are invertible matrices. Then the system reduces to A p y equal to q z or q inverse A p y equal to E z. So, if we now call q inverse A p as t, this becomes t y equal to z, t equals to q inverse A p. Now, we can ask, can we make T diagonal? That is, now we are asking not the same P to be used for both x and b transformations, but we use a different transformation for b and a different transformation for x and then try to convert the equation in terms of these new variables. And if by chance we can find a q and a p such that q inverse A p is diagonal, then we have a diagonal system for y and therefore, can be easily handled. And once we have a diagonal system for y and we have handled it, we have naturally got x because x is equal to p y. Now, the answer to this question that can we make T diagonal, the answer is yes. Given any matrix, of course, reasonable conditions on A, we will put the right framework, but generally we can say the answer is yes. And therefore, this gives us a better handle on the system by using two different coordinates, one to transfer the unknown x, the other one to transfer the known b. Now, you see that the transformation for b involved the matrix Q. Now, in the case of a rectangular system, B will be m by 1. So, we can choose Q to be an m by m matrix and x will be n by 1, we can choose P to be an n by n matrix. So, we have one transformation again for the unknown and one transformation for the known B, and then we would ask a question whether Q inverse AP is almost, we can't ask whether it is to be diagonal, because now since A is rectangular, Q is m by m, P is m by m, the resultant will be an m by n matrix. We can't talk about a diagonal ability of a rectangular matrix, we would like to ask something like almost diagonal. The idea of what this almost diagonal means leads to the notion of singular value decomposition. So, therefore, summing up, what we have is that we have a system of equation which we can analyze by reducing it to the simplest system, and the simplest systems are the diagonal systems. In the case of the square systems, where we have number of unknowns equal to the number of equations, then we can do two things. One is we can reduce the system to a diagonal system by using two different transformations, one for the unknown x and one for the known b. But if you want the same transformation for both b and x, then we may not be able to diagonalize, we may nearly diagonalize it and then try to analyze system. This leads to the two notions, this SVD or the singular value decomposition, and the other one, the Jordan canonical form. Now, this gives us roughly the idea of the problems that we will be handling in this course. The theme, the main theme will be solving systems of equations. This would amount to studying the structure of a matrix, which would then lead us to the generalizations of further linear transformations on vector spaces and all, but the motivation comes from solving a system of equation and how to reduce it to a simple